बट हम स्टार्ट कर सकते हैं, उन्होंने बोला।
यस सर, इसीलिए
जी। तो आप क्या चाहेंगे, मैं स्क्रीन शेयर करूं या रुक जाऊं थोड़ी देर?
सर अभी 10-5 मिनट आप रुक जाइए सर, थोड़ा सा इंट्रोडक्टरी सर हो जाए तो फिर।
ठीक है जी।
गुड इवनिंग वन एंड ऑल। टुडे चीफ गेस्ट एंड डिस्टिंग्विश्ड स्पीकर प्रोफेसर सुनील गुप्ता सर, IAPT president and other office bearer, members and office bearer of regional councils and sub-RC, fellow teacher, dear student, Professor Ajay Bhattav sir, Professor Bhanu Prakash Singh sir, Professor P.P. Pathak sir, Professor Deshmukh sir, and other distinguished teachers from all parts of the country. It is an honor and pleasure to extend a warm welcome to all of you today evening in this last lecture of June month webinar, which is organized by IAPT to celebrate International Year of Quantum Science and Teaching Technology 2025. I welcome all of you on behalf of IAPT, Regional Council of Uttar Pradesh, Sub-Regional Council of Kanpur, and my personal behalf. It is matter of privilege for Sub-Regional Council Kanpur to host this June month webinar with such prestigious academician and physicist. It is matter of privilege for Sub-RC Kanpur to host today's speaker, a leading luminary in the field of astroparticle physics, Professor Sunil Gupta sir, who is currently senior professor and Raja Ramanna Fellow at TFR Mumbai. Professor Gupta sir is currently serving as President Designate of International Union of Pure and Applied Physics since January 2025. It is not merely your personal achievement, sir. Rather, it is an honor for whole country, and we feel proud on you. Professor Gupta, sir, leads a team who develop highly sensitive detector under India-Japan collaboration. He is visiting professor at Chuba University in Japan since 2019. He is represented several national and he is recipient of several national and international awards. Please join me to welcome Professor Gupta sir with a big applause. I hope today Professor Arun Kumar Brower sir is going to chair this session and he is going to join us shortly. So I will welcome you later. Now I invite Professor Ahluwalia sir for his remark.
Oh, thank you, Professor Manoj. And I think it's a proud privilege for us, for IAPT especially, that Professor Sunil Gupta is there with us. In fact, I feel privileged that this evening we are going to have a wonderful lecture on the indigenous efforts of India in the community of scientists. I think that's a very big achievement for us. I would also like to tell the honorable members present here that after Professor Homi Jahangir Bhava, Professor Sunil Gupta is going to be the chairperson of International Union of Pure and Applied Physics. Already he has been designated for that. That means he has been elected and he will be taking the charge in the month of January 2026. Sir, from IAPT family, we extend our heartfelt congratulations to you and wish you a very, very successful innings on the international scenario. It's a matter of pride for us. And I would like to tell the honorable members here that lately I was listening to and I was part of a felicitation program which was organized by TIFR alumni in TIFR itself, where that was a kind of uh, a kind of a satisfaction to see that how Professor Sunil Gupta is respected in his peer group. And there were 4 Nobel laureates who came there and shared the kind of contribution which Professor Sunil Gupta has made in the field of cosmic ray. And the background picture which you are seeing of Professor Sunil Gupta is a sole effort of Professor Sunil Gupta in establishing at UTI this cosmic ray detecting facility, basically detecting particles itself. So welcome you, sir, and we hope that you will always be there with IAPT. I would also like to tell the honorable members that this year we are having International Conference of Physics Education in either Mohali and IIT Ropar. And I must thank Professor Gupta that India could get that meeting and support from IUPAP because of sir's presence there in the IUPAP. So welcome, sir. Looking forward to your lecture. Thank you.
Thank you so much. Okay, so
share कर सकते
अच्छा जी.
Sunil, you are the co-host already. You can share the screen.
Yeah, okay, I will do that. Just 1 second. Can you see my screen?
Yes, sir. It's visible.
Okay, thank you. Thank you, Professor Ahluwalia. I'm really grateful for this invitation because it is our teachers who actually prepare the next generation of students. And without you, none of us would be doing any scientific research, whether we are in university system or in institutional systems. We all depend on your great work. So the theme that I have chosen is a bit unusual, and it more relates to my journey as a physicist rather than anything else. So the title of the talk is Impact of Indigenous Technology for Probing the Interplanetary and Atmospheric Phenomena via the use of cosmic rays and their possible benefits for the society. Benefit part I have put in because most of the time we do get asked this question, what is the user doing fundamental science? And I'm really proud to be talking to you, the august members of Indian Association of Physics Teachers. And your mission is very noble to upgrade the level of teaching and teachers of physics and related areas at all levels to pool and mobilize the talents and resources of teachers in the national perspective. The picture you see is actually at the conclusion of 33rd General Assembly, where I was elected. And so let me move on. This is a face all of you are familiar with, that of Dr. Homi Jahangir Bhabha, who was the founder of TIFR. So once I joined TIFR in 1976, soon after completing my MSc in IIT Delhi, where Professor Ghatak, who is there in the audience, was one of my teachers, I found it very strange place because people were always arguing with each other, discussing, debating, and very rarely agreeing on anything, except they all agreed on one thing, which I found again very strange, that how great a scientist Dr. Homi Bhabha was, what a great visionary he was, and what a great identifier of talent among youngsters and for nurturing them into leading scientists and leading scientific leaders. So this is something that I heard, and that's got me really worried because I knew that I did not have any great talent, and I certainly did not have any vision. So I made two choices. First, I decided that since just about everybody else in TIFR was more talented than I was, that I'll work with people like them so that I can learn something in the process. And one of my seniors was Professor Arun Grover, who was 4 years my senior. And I really looked up to him. I still look up to him now because he is a man with great ideas and, perspectives. So it's always a pleasure to work with him. And then second part was that I did not understand what vision meant. So I interpreted that it essentially meant that you should have a long-term thinking. So I decided I will not work on an activity which is ongoing because I chose experimental physics. I decided I'll work on an experiment which is being planned, and I will work on building the instruments or detectors, testing them, installing them, troubleshooting them, and then collecting data from those instruments, and eventually, after analysis of data, publishing papers. So that became my motto. As a consequence, I could not do too many experiments. In my lifetime in TIFR, I think I did only 3 experiments. That's it, over 44 years. So that sometimes bothered me also, because many of my talented colleagues will work on 1, 2, 3, even 4 experiments parallel. And I found it was impossible for me to do. But, everybody chooses their own path. So this is the beginning, an earlier picture of myself and my mentor, Professor B.V. Srikantan, who also happened to be the director of Tata Institute of Fundamental Research, who had recruited me. And we were working on what is known as an atmospheric Cherenkov telescope. It is nothing but a bunch of mirrors. You see them, parabolic mirrors, which are mounted on a system so that they can be rotated and they can track a star. Because Earth rotates from west to east. As a consequence, the stars appear to move east to west. So we have to just track in a direction. Now, normally the motion is a little bit complicated, but Ooty happens to be very close to equator. Its latitude is only 11.4 degrees. So if we put one axis of rotation parallel to Earth's axis of rotation, then all we have to do is rotate at the speed of rotation of Earth, and the object will stay in focus for anywhere up to 4 to 6 hours. So my first task that was given was, on the left, you see a picture where there was a gearbox, and I was assigned the task of calibrating it and making sure it works as expected. And soon I found it actually didn't work. It was either going too slow or too fast. It took me more than 2 months to figure out what the problem was. And the problem was the instrument was designed to be balanced, which means, the center of mass would pass through the axis. But the moment you rotated the mirror in different direction, the mass distribution will change and it will become unbalanced. And as a consequence, the shaft which was rotating the whole system would get twisted. Even though it was 2.5 centimeter diameter steel rod, it was getting twisted. So once we knew the problem, solution was very easy to fix, and we did it immediately. It took only a couple of weeks, but that gave me immense satisfaction because I solved a real life practical problem. Now, these observations were done in our laboratory, what was then known as Cosmic Ray Laboratory, which is located in the campus of Raj Bhavan, just inside Botanical Garden. If any one of you have been to Ooty, would have certainly visited Botanical Garden. But the site was too small and was, because of increasing tourism, was getting a lot of light. So we could not make observations in the night, which depended on clear, dark, moonless nights. So we decided to move to a remote site. And this remote site was 10 kilometers away in the premises of Radio Astronomy Center, which was pitch dark. Not only it was pitch dark, it was in the midst of wilderness. So we had, wild animals like wild boars and deers, etc., go running by, and of course monkeys and all kinds of smaller creatures were there. So my first task, which I was assigned, was to construct a laboratory building. Now, as you know, a physics student doesn't actually learn how to do civil engineering. So I was assured by my thesis advisor that you be there, make sure things go on time, but there'll be a civil engineer who will come along and actually do the supervision. It turned out the civil engineer will show up once in a month or 2 months. So I became de facto civil engineer. So I worked almost for a year to get this building. You see this 60 square meter structure constructed. Below is the inside view. And you can see, all these electrical conduit pipes are running. This is the area where control room was set up. And even after 44 years, the building still stands. If we do a little bit of repairs and sprucing up, it can still be used. But there was another complication. You see, because it was a remote site, it was hard to get labor. And these were also the time of controls. So everything was controlled, cement and all the construction material. You had to get permits and whatnot. So my task became very difficult. But it so happened we had a Jeep. This is not the one, but of this kind in the lab, but there was no driver. So Professor Srikantan, our director, was a very visionary man. He said, does anybody know how to drive? So I was the only driver in the lab. So I raised my hand and I was tested for my driving skills and duly authorized. So I became a full-time driver in 1977. And till the time I retired in 2020, I was a driver in TIFR, which gave me immense pleasure. But more than that, I could transport the labor in the morning, take them back in the evening. Sometimes when we ran out of cement or some other construction material, we would transport that also. So that was a great learning curve for me. And 3 years later, I got my PhD thesis. So I was very happy about it. And, this is life teaches you so many lessons. And I think it was very beneficial for me. Okay, so then I moved to US to do some postdoctoral work at a place called Fermi Lab in 1983. And I worked again on a instrument. Now, this was being done at the newly constructed Tevatron, which is supposed to accelerate protons to energies of 1 tera electron volt. And at that time, it could only reach 800 GeV. And we were studying jet production, high PT jet production in p-nucleus collisions. So for that, we needed to construct a forward hadron calorimeter. And this is the picture of that hadron calorimeter that I worked from the beginning till end. And it did its job. We got some publications, etc. And I was quite happy about it. Then 10 years later, I took another sabbatical. And this time I went to NASA's Goddard Space Flight Center. And there I worked with this group of wonderful people. They came from different nationalities. This is our team leader. And we built what is known as a magnetic spectrometer, which is just a fancy term for the fact that it has got a superconducting magnet, but it's an air core magnet. So magnetic field spreads all over the place, because you can't afford to send in space an iron core magnet, which becomes too heavy. And then, of course, it has a bunch of detectors, which actually give you position of each particle as it goes through the magnetic field. Now, if they are positively charged particles, they will bend one direction. If they are negatively charged, they will bend the other way. By measuring the positions, you can determine the momentum of each particle. And also, with the help of calorimeters, you can measure the energy. If you know the energy and momentum, you can find the mass and identity of particles. The primary objective was to determine the abundance of radioactive beryllium-10 nuclei in cosmic rays. You see, cosmic rays, as they propagate in space, they interact in interstellar medium, and they produce all kinds of spallation products, including beryllium-10. Now, beryllium-10 is very interesting because it has a half-life of about 2.5 million years. So it tells us about the evolution of cosmic rays over time scales of millions of years. So this was something I did. But majority of my career, of course, was spent in UT, working on cosmic ray detector. This is the view of which you see also as my screensaver of the cosmic ray of the GRAPES 3 experiment, where we also invited our Japanese colleagues to join us, and they have been equal partners with us. Now, the unique thing about this picture is everything you see here is built by the members of the collaboration, with the exception of this bus here. So whether it is buildings or these detectors, these white cones you see, these each is a 1 square meter area plastic scintillator detector. The scintillators were developed in the lab. So we made more than 2,000 of them. Proportional counters, we made 8,000 of them, which are actually kept inside these white squat buildings. I'll show a close-up of it soon. And then, of course, all these detectors is fine, but then you need also to process the signal. Now, what used to happen till that time, till 1998, when we really started installing detectors, is that we used to import all these things, plastic scintillators, etc. And then in 1998, Pokhran 2 explosion took place, and the advanced countries banned the sale of plastic scintillators. So I decided to focus on development of plastic scintillators, proportional counters. And the electronics also was a challenge because much of the electronics everybody used to import. And the cost of electronics used to be typically, if you need an amplifier, you need a pulse shaper, you need coincidence units. Each channel would cost about $100 or 100 euros, which is okay for Europeans and Americans, but for Indians, it's too expensive. So we decided to develop that also. And then to record all that data, we needed data acquisition systems. So we developed those. And finally, we had to analyze data. We found it was much cheaper to build your own computer clusters. And that is what we did. I didn't do everything. My colleagues did. But before we selected this site, we reached out to Professor Govind Sarup, who sadly passed away in 2020. He is basically the father of radio astronomy in India. And Professor Govind Sarup was somehow very kind with me. I didn't know why, because for a long time I used to go and bother him by asking him telescope time, because Uti radio telescope was the premier instrument in India in the 70s and 80s. And he used to always, give me time. And much later I learned indirectly, the reason he was kind with me is he liked the fact I work with my own hands. And since he was a guy who built things with his own hands, including radio telescope, he particularly liked people who do work with their own hands. He didn't very much like people who just sit on the computer. So that was a great advantage. And of course, I was always a beneficiary of his suggestions and ideas. This experiment started in 1993. The data collection began several years later. As you can see, it's a massive effort, and it continues till today. Now, as I mentioned, I always worked with excellent people, and that extended to all walks of life. Here is a picture of my colleague, Mr. Rao, who was our civil engineer. Every single structure you see in Grapes 3 site has been built by this man, whether it is civil structure, buildings, detectors, stands, anything mechanical or civil has been done by him. None of us could have succeeded in doing this experiment but for the dedication and effort of Mr. Rao. And the second person who really gave life to our lab, who did all the landscaping and who was a great horticulturalist, is Mr. Harun, who was our gardener. And over a span of 25 years of his service to our institute, he used to participate in annual flower show, which was a very competitive event in Uti, and used to win large number of cups. So at the end of his 25-year career, I asked a photograph to be taken with all his cups, and we counted 215 cups he won over 25 years. So on an average, 7 to 8 first prizes every year. So here was a champion gardener. I think these are the people who he enriched our life, and Mr. Rao made our life possible. Okay, coming to, since I mentioned plastic scintillator, this is something which is very important. Now, I started doing this in 1998, as I said, after Pokhran 2. And we ran into a lot of problems. We bought the raw material, but we could not turn into plastic sheets. The challenge is as follows. You see these, you see these 5 pictures. This is a sheet of plastic which is 1 meter long, about 25 centimeter wide, 50 centimeter wide, and 4 centimeter thick. Now, if I put a newspaper at one end, you should be able to read from the other end. So it has to have very high transparency. That was a challenge. Even if you take the best quality glass, optical quality glass, you please try to look through 10 centimeter of it. All you will see is either green or dark blue color. But in this case, you can actually read anything across, which means its attenuation length is of the order of a meter. So this took 3 years to complete. I still can recall the day it happened, because each trial used to take about a week or more. And after 71 unsuccessful attempts, we succeeded on 72nd attempt, and we got perfect scintillators, which are as good as anything that anybody can provide anywhere in the world. Okay, and our cost is probably not more than 25-30% of importing them. So this is a development which made our experiment possible. Not only that, you see, because we have built it ourselves, we can customize it. So about 10 years back, a group from Bhabha Atomic Research Center approached me and said, we need a radiation monitor for a very critical national application. I can't go into details of that. And can you provide us a working system in 3 months? I said, look, what you're asking, I have to first do a prototype, and then we have to test it, and then we have to make the final design and test it and then supply. He said, please do something. It is very important for us. So I said, okay, we'll try it. And we did try it. And we couldn't do it in 3 months, but we did it in 4 months. From the time we were given approval to the time it was installed in BRC was exactly 4 months. Of course, the director of BRC and the chairman of Atomic Energy Commission of India were absolutely ecstatic. And that particular instrument generated more goodwill for Tata Institute of Fundamental Research than anything else that was done before. And while I was doing all this development, my scientist colleagues used to come and say, why are you wasting your time making instruments? This is not the job of a physicist. It is not the job of a scientist. This is the job of a technician or an engineer. You should be doing real science. And I used to just ignore them because I knew if we did not succeed, we cannot do science. We could not just afford to do these things. I could go on and on. I could give a 1-hour talk on how we developed and what are the advantages of scintillators, but I think that is not the purpose here. But now it is used in many, many institutions and universities in India, and of course in many institutions in the Department of Atomic Energy. Even space program, people are interested in using it. The second thing is proportional counter. These are 6-meter long tubes, which are welded at both, which are clean, and both ends we weld steel plates and thread a 100 micron diameter tungsten wire, which acts as anode, the outer body acts as cathode, and inside you fill a special gas mixture devoid of oxygen. And then you can use it as a proportional counter. And on the bottom right, you see the signal from this counter. What you see is the signal due to cosmic ray muons, which are passing through the detectors. But what is remarkable is earlier, we never had this flat background at low pulse heights. It used to be rapidly rising background because of noise. But here it's virtually noise-free. And we see this peak, which is due to K-alpha emission. These tubes are made up of iron 56. And when you knock out an electron, a muon knocks out an electron from the K shell, the one from L shell jumps down and produces a 6.4 keV line. That's why you get a sharp peak. And this electronics was developed by Mr. Ramesh, who did such a phenomenal job that our Japanese colleagues were impressed. They said, this is much better than what we were able to design. So you see, once we have developed the confidence among our colleagues that they can succeed in doing anything, now they're confident they can do anything under the sun. And that has been the greatest benefit of doing indigenous development. So I gave you 2 examples of detectors. I give you 1 example of electronics. Let's move on. This is the muon telescope. Now, that word telescope is slightly maybe considered a misnomer here. You see, what happens is we have 4 layers of proportional counters. They are arranged in layers, and there is in between concrete. So what happens is this layer is arranged, let's say, in one direction. This is in the perpendicular direction. Now, if a muon goes through, let's say counter number 12. So I know its location within plus minus 5 centimeter because the width is only 10 centimeter in, let's say, Y direction. But I don't know its coordinate in the X direction. But if I look at the bottom layer, I get the X coordinate. So I get 1X, 1Y, second X, second Y. So I have 2X and 2Y measurement. If I combine, it's like having 2 points in space. I combine 2 points, I get the direction. And by reconstructing these, which are discrete directions, you create a map of sky, which is in form of 169 pixels. Now, your mobile cameras have millions of pixels. This is only 169 pixels. So you might wonder, what kind of telescope is this that has only 169 pixels? My answer is, all other telescopes have only 1 or 4 pixels. Compared to 4 pixels, 169 pixels is a huge improvement. And that's why this is a very important telescope. And total area is 560 square meters, which makes it the most sensitive muon telescope in the world as of now. Okay, so when I talk about all this sensitivity, I should give you evidence. I cannot just go on claiming this is good, this is best and all that without backing it up with facts. So here is a plot. So this is from the data itself. This is when the atmospheric pressure is unchanged, 0. And this is the deviation from mean atmospheric pressure. So when you increase the pressure by 1 hectopascal, which is about 0.8 millimeters of mercury, you see the muon intensity drops because the atmospheric pressure increases, more muons are absorbed in the atmosphere because they are produced in the atmosphere. So there's more matter in the atmosphere, they get absorbed. And similarly, if there's less pressure, the number increases. From this fit, we can determine what is the slope. And from the scatter of these points, which is so small that you cannot see it, you can determine what is the uncertainty in that pressure. So now, as we sit, we know that as you go to higher elevations, atmospheric pressure drops. So the atmospheric pressure near your chin is higher than atmospheric pressure near your top of the head. But do we bother about it? No, we don't. Because it's insignificant compared to even our blood pressure changes, right? That is 40 millimeters of mercury. So, but this instrument is so sensitive that even a change in atmospheric pressure corresponding to 20 centimeter height will introduce a significant change in muon intensity that we can detect it. That is the sensitivity of this telescope. Then it's also sensitive to atmospheric temperature. If you're interested, I can explain in great detail how it comes about. But this was a prediction made in 1950s. So if these muons are produced in the upper atmosphere and the upper atmospheric temperature changes, for example, in summer it is hotter, winter it is cooler. It changes only, you see here on the x-axis, it changes by only plus or minus 1 Kelvin in a year. And therefore, that change is adequate enough to introduce a huge change in muon intensity. So our sensitivity is any change of 0.06 Celsius causes a significant change. So it's a very sensitive thermometer of atmosphere, very sensitive barometer of atmosphere. The next is, after making all these corrections, atmospheric pressure and temperature, now atmosphere doesn't bother us, right? We have taken it out of equation. Now we ask the question, what is the muon how does the muon intensity depend on time? So you see this blue, light blue color shows the change in the interplanetary magnetic field. This cannot be measured from ground. This is measured by satellites such as Aditya L1 or other NASA and European Space Agency satellites in nanotesla. So you see it is undergoing changes. And the dark line shows the changes in muon intensity measured by Graves 3. You see the two follow each other almost uncannily. And from this correlation, we can determine that we can easily detect changes in interplanetary magnetic field, which are as small as 0.1 nanotesla. 0.1 nanotesla is million times smaller than geomagnetic field or Earth's magnetic field. So it's a very sensitive magnetometer of interplanetary space. And there are two more things we can do that I'll come to in a moment. Since I don't have time to get into details, basically, it acts as a very effective atmospheric voltmeter. We can measure voltage across thunderstorms of voltages as high as gigavolt. And it can detect current that is produced by muons traveling down the atmosphere, which are as small as 1 femtoampere with an accuracy of 1 attoampere. As you know, you are all physicists, that 1 attoampere is just flow of 6 electrons per second. So that's how sensitive our instrument is. Okay. Now, I want to, share some of the comments. Professor Ahluwalia mentioned the comments of some of the great scientists of our era. So this is, of course, a picture of Professor Ting in his earlier days. He is much older now. Professor Ting, I don't know how he came to know about my work, but he has been very appreciative. And as I will share later on, that I had very close interaction with him and continue to have close interaction with him. And on this event, which Professor Ahluwalia alluded to, which is also available on YouTube, he stated this, that I believe the development of high quality detectors and electronics in India is his most important scientific contribution, because the quality of physics depends on the sensitivity of detectors. And I will share a story at the end, which is very fascinating, which Professor Ting told about his personal life. So time permitting, I would like to share with you. This is Professor Takaki Kajita, who won the Nobel Prize in 2015. I forgot to mention, Professor Ting won the Nobel Prize for the discovery of charm meson, that is so-called J particle. And Professor Kajita won the Nobel Prize for discovering the neutrino oscillations, which actually solved a very long-standing problem, which was there for almost 40 years. You see, what had happened is, in fact, when I joined TIFR, everybody used to talk about so-called solar neutrino problem. What had happened was that there was an experiment by a scientist in the United States, Raymond Davis, which showed the number of neutrinos we are getting from the sun is only 1/3 of what we expect. And this was a great surprise because everybody believed we understand how the thermonuclear furnace inside sun works. They are very accurate model. They are able to predict to 1% accuracy. Yet the number of neutrinos are only 1/3. And for the longest time, people didn't believe this to be a real effect, but Professor Davis kept gathering more and more, data, and finally it became irrefutable. And in 1998, Professor Kajita found the explanation for it, for which he was awarded Nobel Prize in 2015. And he has been also a very close friend of mine. So, in 2023, they had awarded me this O'Kelly Medal for contributions to solar terrestrial physics and for my services to cosmic ray community in India and worldwide. So it was nice to hear from them. And this is the person I greatly admire, Dr. Anil Kakodkar, chairman of Atomic Energy Commission for 9 years, and also the architect of Pokhran. And I have told Dr. Kakodkar that it was such a wise decision to do that. Had we not done that, we would have been in great predicament, seeing what has happened to certain countries as we watch events unfolding elsewhere in the world, that having the nuclear deterrence is a very, very important asset. So Dr. Kakodkar, he has been one of my mentors. I have known him for almost 25 years. And in fact, I showed him our fledgling efforts to develop plastic scintillators. And he was very encouraging. And he made this statement that, that we make the best quality plastic scintillator, which have helped our research, but also helped many programs of Department of Atomic Energy. And there was also a program that I used to run where we used to get engineering students to develop advanced instruments through involvement of faculty. So we'll give a project, the students will work on it, and then they will complete their project, go away. Then the next batch will come and take it up from the place where the previous batch had left off, and continue over a 2 or 3 year period. The project will get completed. So this was a great effort because it was a great help, because otherwise, we could not afford to spend so much money doing development activity. Now, let me come to some scientific results. You see, as scientists, we design experiments to study specific phenomena, and which is fine, but oftentimes we get unexpected surprises. In fact, those unexpected surprises are much more important than what we had originally sought out to do. So one of the results we got was a short-term weakening, 2-hour weakening of Earth's magnetic field, but due to a passing solar storm, which got recorded because of our Muon telescope, which is extremely sensitive, by recording a burst of cosmic rays. You see, when I say burst, you have to be careful. This burst meant the intensity of cosmic rays increased only by 1%, but our error in measurement was 0.01%. So this was a huge effect for us. Everybody else in the world couldn't detect because their sensitivity was 1 or 2%, so they could not see it. And this phenomenon is very important because it has the potential to disrupt electrical grids and communication satellites. So this was published in PRL in 2016. It attracted a lot of attention. I should tell you in a moment. And the second important thing was that we found that thunderstorms generate electric potentials as high as 1.3 gigavolt. And they store massive amounts of energy, of the order of terajoules, which is enough to power a city, let's say Mumbai or Delhi, for half an hour. And to sustain this thunderstorm, voltage, you need a generator, thermal current generator, which supplies at least 2 gigawatts of power. Of course, both these phenomena are very important for the obvious reason. First one, because of its impact on electrical grids and communication satellites. And the second one is because thunderstorms are the leading cause of death by natural phenomena. And in our country, we lose of the order of 2,000 lives every year due to lightning strikes, especially during monsoon season. These are the reported numbers. The actual numbers could be even higher. Okay, so the first result actually received worldwide attention. And, it was reported in 119 countries. In fact, dozens of YouTube videos were generated. There were more than 1,000 reports in 37 languages. And 2 of the videos have, 3 million, 500,000 views. So my students, one of them is sitting there, Anuj, they basically decided to paint the world map in tricolor wherever there was a report. So except for black marks where there was no report, you can see how widespread the coverage was of our work. And this was regarding the thunderstorm work that also received massive coverage. We didn't do anything, actually. It was all done by physical review letters. They reached out to all the journals, the Nature, Science, New Scientist, National Geographic, all brought out overall more than 100 reports. But now this is something very close to my heart. You see, and it's very apt to be speaking to all of you. These 2 gentlemen, the one on left is Julius Elster, and I don't know his name. His last name is Geitel. So Elster and Geitel were high school teachers in Germany in late 19th century and early 20th century. They were remarkable scientists. They did their PhD and they were offered positions in universities, professorship. They refused. They chose to work in high school as high school teachers. And they carried on experiments on electricity. They were such gifted people. They are the ones who explain the mechanism by which thunderstorms, get charged. You see, you can understand that, one of the early measurements was by, for example, Benjamin Franklin. We all know about kite experiment. That there is charge which is present when thunderstorms pass by. But how does the charge separation happens was not understood until these gentlemen explained the phenomena as due to basically collision between water droplets which are rising due to thermal currents and the snow particles which have already gone up and frozen are falling down. Their collisions cause charge separation. And the charge separation is what leads to generation of electric field and electric potential. It took 150 years after Franklin's discovery for them to come up with this explanation. They're truly gifted scientists, and they used to interact with leading scientists of that era. And I have just listed only 11 of them who were, all great names. We all know them: Roentgen, Becquerel, Arrhenius, Ramsey, Leonard, Thomson, Rutherford, Wien, Planck, Nernst, Hahn. 6 of them Nobel Prize winner in physics, and 5 of them Nobel Prize winner in chemistry. Okay, and of course, Roentgen was the first Nobel laureate in history. So you see, this is the strength of our teachers, that they, despite not having any great facility, just on the strength of their ideas, they could do these wonderful experiments, which attracted visits by all these greats. I have not mentioned other great scientists, because then I would need few more pages. And despite all the persuasion, they never left high school. Okay, so now I'll come to my innings post 2020, which I call second innings. So as Professor Ahluwalia mentioned, my Japanese host, Professor Iyoshi, who is Chancellor of Chubu University, he used to head the fusion program, one of the fusion program. I don't know whether it was magnetic fusion, confinement or inertial fusion. He used to head one of the fusion programs of Japan. And then he became the Chancellor of Chubu University in close to Nagoya. And he appointed me a visiting professor. So I go every year to Japan. We work all day long. We eat together, sit together. And then we analyze data, we write papers, etc. And of course, we go on tours also to visit various labs. Here is Mount Fuji in the background. And this has been one of the most productive collaborations. For 35 years, we have worked together without any arguments or quarrels. I think it was one of the most successful collaboration. And I'll explain to you in a minute what it meant. So you see, in 2020, Professor Kajita was invited by our ambassador to Japan, to Indian Embassy in Tokyo. Professor Kajita at that time was director of Institute for Cosmic Ray Research of the University of Tokyo. And Indian ambassador, Mr. Sanjay Kumar Verma, who incidentally later on became the High Commissioner to Canada and had to be recalled for, the reasons very well during Trudeau era. So Mr. Verma invited Professor Kajita and said that, it is the policy of Indian government and Japanese government to have closer India-Japan collaboration. So he would encourage him to enter into a MOU. And Professor Kajita said, are you aware that we already have a very strong India-Japan collaboration going on in India? And Ambassador Verma said, no, I don't know. So he gave my name and phone number after confirming with me and said, why don't you talk to this guy? So I get an email from Indian Embassy saying that during your next visit to Japan, please drop by Indian Embassy. So I went there and I met Mr. Verma, who was very gracious. It turned out, this will interest Professor Ghatak also. He turned out to be a MTech from in physics from IIT Delhi. He was about a decade after me. He was very respectful and he understood what I was trying to tell. And I explained to him. He said, this is wonderful. Let us have a memorandum of cooperation, a kind of umbrella agreement between India and Japan. And he asked me, what shall I do? I said, well, we are funded by Department of Atomic Energy. So you have to, maybe you can talk to Chairman of Atomic Energy Commission of India. So immediately called up Dr. Vyas, who was then chairman. And Dr. Vyas knew me personally. So he said, yes, I know him and I will facilitate this collaboration as early as possible. But, bureaucracy has its own way of functioning, both in India and Japan. So it still took close to 2 years. Finally, the then director of TIFR, Ramakrishnan, and Professor Kajita, they signed this agreement on March 31st, 2022. This date is very important for me because this was the last official document Professor Kajita signed because he decided to step down as director on that date. So this was very important. As I mentioned, Professor Ting had been inviting me to visit him. Now, he leads a collaboration of 500 scientists. And they have a big magnetic spectrometer in space, which weighs 7.5 tons. It is sitting on International Space Station. It is one of the largest instruments on International Space Station. So in 2023, June, I visited him. He invited me over for lunch, and after lunch, he said, okay, let's go to the lab. That was a Sunday. But Professor Ting, who was 87 then and now 89, doesn't believe in taking holidays or time off. So we went to lab. I got a tour of his control room because they had to keep track of the instrument 24/7. You see, when you're in space, you go around the Earth every 90 minutes. If any of the systems fail, even for 10 minutes, the system will freeze over and the instrument will not function. So he sought my advice. You see, what had happened is Professor Ting had developed such a sensitive instrument that he was able to improve the measurements which were done before by 2 orders of magnitude. So, for example, earlier measurements had 100% error bar. His measurements have less than 1% error bar. So every time he will publish a paper in Physical Review Letters, it will conclude by saying that this is our measurement and there's no explanation, theoretical explanation for it. So I told Professor Ting, this doesn't give any idea to the reader because you see, you are given the same statement paper after paper. And he said, well, I'm an experimentalist. What can I do? I said, you can do a lot more. First of all, these theories were developed when the measurements have 100% error. Now you have improved the errors by 2 orders of magnitude. But the theories have not kept pace. So we need to advance theories. He said, but I'm not a theorist. Tell me what I should do. So I told that we are going to have next month International Cosmic Ray Conference in Nagoya. And I will ask them to organize a half-a-day workshop or one-day workshop where you have to share all your unpublished data and tell people, tell the community that we invite you to work with us. So he immediately agreed. Normally, he doesn't like to share data with anybody else because obvious reason, data is the most precious thing any experimentalists have, but he agreed. So this picture is when the workshop took place. And I was very fortunate to be awarded with this Kelly Medal. It is Professor Ting, Professor Kajita, Mrs. Ting. This is Professor Sugiyama, president of Nagoya University. In the evening, he took us out for dinner to a vegetarian restaurant because of my dietary restrictions. So we had a great time. And then last year, Professor Ting invited me to Johnson Space Center, where all these astronauts get trained for the critical design review of AMS upgrade. You see, he already has this most sensitive instrument, but he's not happy. He wants to increase its sensitivity by a factor of 3. So he wants to upgrade this instrument, which means launching another 1 ton of instruments by 2 spaceship rockets, SpaceX rockets, and 6 astronauts have to work on its installation. So there was a critical design review taking place. So Professor Ting invited me. So I told him, Professor Ting, I have no idea about this program. He said, oh, it doesn't matter. You come and, if you get any ideas, you share with me. So I happily agreed. I have nothing to do. So I went there. He's taking care of all my travel and other expenses. So I landed up there, and then we had one evening nice party. This is there was another delegation from Taiwan was visiting, and there were a whole bunch of NASA officials. And then in the evening, we had another day. We had a dinner. Here is another astronaut, Luca Parmitano, and see what happened was that when I went there, Professor Ting made a very impressive presentation about the objectives of that upgrade, and I could see that the NASA engineers, while they got a sense of how important it is, but they did not quite catch the exact significance of his work. So I went to Professor Ting and I said that if you don't mind, I would like to elaborate on what you said. And Professor Ting immediately announced that my name, that I'll make the first presentation next day. Anyway, I was not planning to make a presentation. I just wanted to make some few simple statements, but I had to sit through the night and make a presentation, which I did next day, where I likened the cosmic rays, which are the main energy carrying messengers in the galaxy, to the engine that operates the galaxy. Okay, so it is the cosmic rays which serve as the engine, but the photons, which are basically a very small fraction of the total energy budget, they actually effectively represent this exhaust of the engine. So I used the equivalence between an engine and a galaxy. And for some reason, the NASA engineers liked that analogy very much. They live streamed my talk all over them. And then in the evening, a whole bunch of astronauts descended and they wanted to have a discussion. So this is one of the astronauts. He has already spent more than a year on International Space Station on multiple missions. His name is Luca Parmitano. And this is astronaut Slavoj Uznansky. He's one of the 4 astronauts who is right now in space along with our Indian astronaut Shukla. In fact, we had invited Shukla also, but he could not make it because his family was visiting. So Uznansky will be there along with astronaut Shukla. They will return back. This selfie was taken by Uznansky. This lady is the one who trains the astronauts, and this gentleman is the one who's responsible for mission control. This is again Luca Parmitano. It was very interesting meeting these people because they have very different perspective. What I found is that the astronauts, while they're extraordinarily talented people, in fact, the senior astronaut, by the way, Luca Parmitano has also trained Uznansky and Shukla. So he told me, he said, look, we are not engineers, we are not technicians, we are not scientists. Then I asked him, what are you? He said, we are very good operators. We operate the spacecraft, we operate your instruments, we install things, but we don't know anything beyond that. So we would really like to know that. So it was a very interesting conversation. And I found them to be very curious community. And I'll tell you in a minute more about them. Then last October, there was this General Assembly of IUPAP. As I was going, Professor Ting called me and said there is a special workshop being held in Beijing to commemorate the 50 years of discovery of J particle, for which he was awarded Nobel Prize in 1976. The discovery was made in 1974. So I asked who the speakers are. He said, oh, apart from me, there is Sheldon Glashow, who shared the Nobel Prize with Abdus Salam and Steven Weinberg, and David Gross, who won the Nobel Prize for quantum chromodynamics in 2004. Glashow won in 1979, and Luciano Maiani, who is also very famous physicist, along with Glashow and Iliopoulos. He was responsible for giving the so-called Jim mechanism which explains charm production. So I was a little bit shocked because I don't have any contribution in this field. So I expressed my misgivings to Professor Ting. I said, Professor Ting, you're inviting me, but I have nothing to add to what you guys will do. He said, I'm not an expert. He said, that's why I'm inviting you, because you are an outsider. So anyway, I went, and here is Professor Gross, Professor Glashow, Professor Ting, and a whole bunch of other people are there. And on a rest day, we went and saw the old artifacts in Forbidden City being restored. This is Professor Ting and Professor Glashow. Anyway, on the day of workshop, all these guys gave fantastic talks. And finally, when my turn came, I had been struggling with what to say. Finally, I decided, let me put my IUPAP hat on. What does IUPAP mission is? The IUPAP mission is to foster international collaboration, to spread physics. What has Professor Ting been doing? He has been building largest collaborations on Earth for 60 years. He has trained thousands of students who are now leaders in their own right. So I enumerated all these contributions of his, and it was so different from what everybody else that they were very happy. I got a very nice ovation. So let me come to the final part. The task of IUPAP is to assist the worldwide development of physics, to foster international cooperation in physics, and to help in the application of physics towards solving problems of concern to humanities. Now, IUPAP was established in 1922 in Brussels with only 13 member countries. And the first president was William Bragg of the famous Bragg family, who discovered the crystalline structure through X-ray scattering. And and he was succeeded by Robert Millikan of Millikan oil drop fame. Now, one of the things that I am particularly proud of is the role of IUPAP in ensuring there is international cooperation. So IUPAP had passed a IUPAP Executive Council, of which the President is chairman, passed a resolution regarding international conferences. IUPAP, during the darkest days of the Cold War, apartheid, and many other difficult political eras over the past 100 years, has always been able to do things with care and responsibility. First, kept open the channels for scientific cooperation across all political and other divides in the hope and expectation that enhanced scientific collaboration is important to develop improved understanding between different peoples to contribute to world peace. Two, expressed its concern about any activity or intervention, including war, that impacts negatively on our ability to engage scientifically on a global scale. So these are two very important things. And, in recent times, after the Russian intervention in Ukraine, it was said that it will be inappropriate for IUPAP to bar any scientist, especially from a member nation, from any scientific activity, so long as the work upholds the ethics and principles of science in its highest ideals and does not contribute to weapons capability. IUPAP can see no reason to disallow Russian scientists participating in the affairs of Union, and we have not done that. So Russian scientists continue to participate in every activity of IUPAP because we don't believe in banning people making political judgments. We only want to focus on scientific collaboration. I already had a long association with IUPAP. My 13-year journey began first as an associate member starting 2008. then member 2011, vice chairman 2014, and chairman 2017 of IUPAP Commission C4 on astroparticle physics. This is the commission earlier known as Cosmic Ray Commission. Its name was changed in 2015. Before COVID-19 pandemic, as chairman C4, I used to attend executive council and commission chairs meetings. I had attended in Singapore, Vilnius, and London, which were a great learning experience. Now, IUPAP has a total of C1 through C20, 20 commissions, but there is no C7. So there are only 19 commissions, out of which C1 deals with only finances. So it consists of these executive council members. So physics, there are only 18 commissions, and I was chair of one of them. So I had opportunity to interact with fellows, 17 commission chairs, who all came from other disciplines that I knew precious little about. So it was a great opportunity to learn and form strong bonds. So this picture was taken in 2018 in Vilnius, Lithuania. And this picture was taken in 2019 in London, United Kingdom. And I want to especially put on record my interaction with some other stalwarts. The interaction with Executive Council was a learning experience. Past President Bruce McKellar, who was awarded of Order of Australia, the highest civilian honor, and his encyclopedic knowledge of IUPAP rules, bylaws, and traditions made those interactions memorable. I'm still in contact with Professor McKellar. He's always only a one phone call away. And then there is the infinitely resourceful and dynamic, at that time, initially President designate, and then President, and now past President Michel Spiro, who I came to know very closely and learned so much from over the course of past 8 years. Now, Michel Spiro, okay, so the way it works is you serve as President designate for 3 years, then 3 years as President, and 3 years as past President. It's a 9-year commitment. So Professor Michel Spiro started 3 initiatives, which are very important. First one is International Year of Basic Sciences for Sustainable Development, which was during 2022-23, IYPSSD. Given its success, it was, by the way, authorized by United Nations unanimously, United Nations General Assembly unanimously. That has now been turned into an International Decade of Sciences for Sustainable Development. Then one of the things which everybody talks about, that we should involve young physicists or students into the affairs of IUPAP, but it was always a talk. But Professor Spiro took the initiative and formed what is known as an affiliated commission, which is not a full commission, Affiliated Commission 5, which primarily consists of members of International Association of Physics Students. And then Working Group 16, which essentially comprises of physicists from IUPAP and industry, because 80% of physicists work in industry, not in academia or university system. So it's important not to lose that access to that huge resource. The IUPAP centenary was celebrated in 2022, as it was founded in 1922. And there was a panel discussion took place on Asia Pacific region, which I was asked to chair. It was very nice to do that. We would present a unified view from our region, and on to the 33rd General Assembly, which took place in this beautiful Haikou city in China. And here are some pictures during the meeting. I was sitting with Professor Kajita because we knew each other. And this is the same picture which I showed you at the beginning, at the conclusion of General Assembly. And I had the honor to address the 33rd General Assembly on 13th October. And I outlined my priorities over next 9 years. And that basically, there are 2 things which I feel very strongly about. One is that all the talented youngsters are in the developing countries, so-called Global South, while most of the resources and expertise is in Global North. So unless we bridge this gap, now it is not possible for everybody to move to Global North or Global South to come to Global North to come to Global South. So we'll have to find other means of doing it. But it's very important to bridge this gap. That is one thing. And second thing is, which I experienced myself in my lifetime, is there is a constant barrier to travel because there are visa restrictions. So we are working, with International Science Council, which is association all unions, to evolve a strategy and try to put pressure on governments. Of course, governments do not necessarily care about what the academics have to say, but at least we should not leave it to just chance. So now this is an important event. Now, what has happened is that for a variety of reasons, as I mentioned, that we are physics union is represented by International Union of Pure and Applied Physics, and similarly there are other unions like for chemistry, biology, mathematics, biophysics, social sciences, all kinds of area which constitute International Science Council. So I'm a member of one of the committees, and in a recent meeting, the president of ISC said that even though we do wonderful work, we are constantly asked to provide support to United Nations when it comes to policies on climate, on decarbonization, on artificial intelligence, on quantum sciences, you name it, they seek our advice because we have all the experts on our panels. But most people don't know it. So this is something that was there in my mind, that we need to have events which are so spectacular that we can attract large number of people. So I discussed this idea with Professor Ting, Kajita, and Barry Barish. Professor Barry Barish is the person who had discovered the gravitational waves due to merger of black holes, for which he received Nobel Prize in 2017. And also we reached out to Professor Michel Mayor, who discovered the first exoplanet. And they all agreed. So I reached out to my colleagues who are organizing the next International Cosmic Ray Conference in Geneva, and told them that you set aside one day for this event. So what we'll have is lectures by 4 Nobel laureates who will speak about their science, how it is impacting, it is impacting, or how it will impact the society. And then, because it will be held on 19th July 2025, which is the eve of first moon landing 56 years ago by Armstrong and the other guy, I forget the name. Anyway, so that to commemorate that, we'll have this event. So we have also invited 5 astronauts, and it was very interesting. Initially, we invited only 3 of them, but then others came to know, and they started approaching us. So most of these astronauts are Europeans. And then I got a call from one American astronaut that why there is no American astronaut. So we have included him also. And so we'll have a very exciting program. This was to be held in City Center where the conference was going on. Then the CERN, where the Higgs boson was discovered, they came to know about this event. So they offered to host it. And they have very good full-fledged outreach department. So we were happy to have their help. So it is being held in Science Gateway of CERN. They're doing a lot of publicity. And what you see is the YouTube link, which I have already shared with Professor Aluwalia, and he would have shared with you as well. And similarly, I mentioned this to International Science Council, and they were very thrilled about it. I said, you don't always need big budget to advertise your capabilities. All we have to have is a good idea. So if it is successful, I have hopes to repeat this exercise, especially in India. I would like to do that if we can generate sufficient support, because we also need money for travel and for other expenses. This was on the web page of International Science Council. They have put up this. Okay, this is a fascinating picture. This is Professor Barish. So I had consulted him, Professor Kajita. And this is Professor Klaes Fahlender. He was the chair of the committee which decided on, he's an old friend of mine. He chaired the Royal Swedish Academy Committee for Nobel Prize in Physics. This picture I really like because, up to BSc, I studied in Hindi. And this is the director of BRC in 2020 and in 2022. Vishwa Hindi Divas was organized. And Dr. Ajit Mohanty, who is now the current chairman of Atomic Energy Commission, invited me on both occasions to deliver. 2021, of course, there was nothing because of peak of pandemic. So I went there on both occasions and delivered my talks in Hindi, which was very nice. Though they were generous, they said I could use some words of English as well, but I chose not to. Here I want to recall 3 of the stalwarts who have been my benefactors. Dr. M.R. Srinivasan, who was the 5th chairman of Atomic Energy Commission, who passed away in May this year. Dr. K. Kasuri Rangan, who also passed away in April, and Professor J.V. Narlikar. Dr. Srinivasan and Kasturi Rangan played a pivotal role in nurturing cosmic ray research at the Cosmic Ray Laboratory, Ooty. I hugely benefited from their wisdom, guidance, and friendship. Professor Narlikar was just not an eminent scientist, but also a great teacher who taught me. So their passing is a huge loss. These are some pictures of Dr. M. R. Srinivasan. He was one of the earliest persons Dr. Homi Bhabha recruited to kickstart the atomic energy program. So whenever I organize an international meeting, I requested him to chair the organizing committee, which he gladly did. This is 2006, 2008, 2012, and 2016, along with his wife, Mrs. Geeta Srinivasan, who deserves 50% of the credit of everything that Dr. Srinivasan did. This was the visit of Dr. K. Kasturi Rangan in 2017. He spent 3 days with us. And as usual, I would display all my detector development. After I have shown him all these things around, he said, okay, I want to share one secret with you. And said that, when I joined Physical Research Laboratory, Dr. Sarabhai Vikram Sarabhai called me and said, I want you to build a proportional counter. And I replied, I don't know how to build it. He said, go and read in the library and then start doing experiments, trials. And it will take you a couple of months. He said those couple of months turned into a couple of years. But when I succeeded, I got great pleasure, I got far more happiness from that successful proportional counter than I did with Chandrayaan, Mangalyaan, and all other projects that I supervised as ISRO chairman. There's, of course, Professor B.V. Srikantan. He was the third director of TIFR. Dr. Bhabha was succeeded by Professor M.G.K. Menon. And Professor M.G.K. Menon was succeeded by Professor Srikantan. And it was Professor M.G.K. Menon who recruited Professor Grover to TIFR, and I was recruited by Professor Srikantan. He was from my field, and I did not know that you should not bother directors. So I used to barge into his office and ask questions, and he used to patiently explain. He was such a generous soul that, I just could not imagine my TIFR stint without thinking of him. I think next to my parents, he played the greatest role in my life. As I mentioned, I also used to be always his chauffeur. Here he is. And this was during my last visit when he was 93 years old. He passed away at the age of 94, making his evening coffee. He never liked to depend on anybody. These are three great stalwarts, right-hand men of Dr. Homi Bhabha, Dr. M. R. Srinivasan, Professor B.V. Srikantan, and Professor M.G.K. Menon, who also made several visits to TIFR. I came to know him much later in life, but after that, it was amazing to have discussions with him because he had such a broad vision that any conversation would turn into an enriching experience. This is Dr. Anil Kakodkar. I've known him for 25 years. And he was the first person I got hold of during a planned discussion. He had just become chairman of Atomic Energy Commission. I said, would you like to come to my lab? I want to show you what I'm doing. And he came and he skipped the planned discussions. I think the director of the day was not very pleased with me. But anyway, I never cared about those things. The net upshot was that after that, I wanted to talk to Dr. Kakodkar and I called his office and they gave me his personal number. I said, you can call him directly in the morning. Those were pre-mobile days. I said, is it okay to disturb him in his home? He said, yeah, go ahead. So I occasionally used to call Dr. Kakodkar and he will always pick up my phone and give all the time I needed. Many years later, long after he had stepped down as chairman, I asked him, I said, Dr. Kakodkar, why did you give your personal number? And he replied, he said, you give unfiltered opinion. And when you want to make decisions, you don't want too many filters on the way. So I consider him to be a mentor. But he thinks of me as friend. So we kind of argue about it. But that's it is. These are four of my friends, very dear friends. Professor Shivaji Raha, former director of Bose Institute. Professor Arun Grover, you all know. He's another great friend and mentor. Professor Naveen Singhi, great discrete mathematician of India. And man of very strong principles. And Professor Tariq Aziz, who's alumni of AMU. Another very dear friend. And these four have been the rock of support during my dark days in TIFR. When everybody felt I was wasting time, these people sort of, stayed true friends. So I cannot forget them. And of course, I would be amiss if I did not express my grateful thanks to non-academic staff in the institute for their contributions, which were critical, This includes every service, scientific, engineering, technical, administrative, and auxiliary staff. Because I always used to make it a point to talk to these guys before asking them any work. I used to explain why I'm asking them to do some things. So as a consequence, I never faced any problem in TIFR. People used to complain that, oh, their paperwork is not moving, their things are not happening, but my things happen all the time. Even after I've retired, I just have to make one phone call and my job is done. When I go to TIFR, I get very warm welcome from everybody. And that, I think, is my greatest asset. And of course, nothing will be complete without mentioning the Grapes 3 team, which is a large number of people. And of course, it doesn't include everybody. There are many, many names which I've missed out. There's just a sample of people. And finally, my wife, who played a very, very important role. And like everybody else, she was better than me in everything, with the possible exception of physics, including taking care of our children who are now grown up. They have their family of their own. And I would like to stop here. And thank you so much for your attention.
Very nice.
Thank you, sir, for a very insightful lecture. Before opening the session for question answers, I would like Professor Arun Kumar Grover sir with us. I would like to welcome Professor Grover sir on the behalf of IAPT and Sub-Regional Council of Kanpur, because there is no more time, so we'll go ahead for the question answer session with the kind permission of Professor Arun Kumar Grover sir, who is the today designated president of this session. Professor Grover sir.
Anyway, first my apologies. I couldn't join you in the beginning. I was caught up in another meeting from which I could not leave immediately. So I'm very happy that I could finally come and join and listen to this wonderful talk by Professor Sunil Gupta. And I think I should first let others ask the question before I say something more about Sunil and the background of
I request you to just conduct the question answer session as the chairman of this session.
Okay. So who are the persons who have raised hands? I cannot see it at my end. So please let me know who have raised hands to ask questions.
Okay, sir. I will check.
Professor Ahluwalia, who all have raised hands to ask questions?
As yet, sir, there is no one as such. But may I begin, sir?
Yes, please go ahead.
So thank you very much, Professor Sunil. It was a great learning experience to listen to you. There were many lessons which personally I can take home. One was the quote which you gave of Professor Govind Swarup. That was, I think, a kind of a lesson which we need in our classrooms also, in our labs also, because we are losing interest in working with our hands. And in fact, IAPT has lately got a tagline that IAPT believes in hands-on, minds-on experiences. So I think that is one of the very interesting things which I could get from you in this lecture. But I think it was a grand journey in which you not only shared your journey, but you also shared the journey of the Department of Atomic Energy and your association in collaboration with the scientific community all around the world. When I was really listening to you, I was just wondering how IAPT can also be part of such collaborations. And I'm happy to tell you that recently with this GRAP group, IAPT has signed a memorandum of understanding to organize maybe online workshops and lectures and collaborations. And I think it definitely tunes very nicely with the message which you tried to give us in this. Another very interesting thing which was there was this, that you showed us that if we are determined, I always put it like this: where there is will, it is not there is way, it is not even railway, it is internet highway which is available to us these days. Connecting with people is not at all difficult these days. We can connect very easily. And we are witnessing that in the last almost for the last 3 years on the IAPT platform also. We have been able to reach out. Can you imagine that Professor Ghatak came and gave series of lectures to us in the past 3 years? Who would have
Oh my God.
imagined that we will be sitting in his classroom? So we believe that our IAPT, which has got 10,000 members, we are like a typical university.
Yes.
And our university is in the cloud. And this is how we conduct lessons for our members. This is also something great. I would request, we would really like to interact more with you from IAPT.
Sure.
And maybe if
Absolutely.
we can do small things, the way we organize these days, for example, we are carrying out a very interesting program which started from Jammu and Kashmir. And we are in that program trying to go to each and every corner of the country, all the states we are going to cover. It is under a program which we have in IAPT called National Anvishika Network of India. Professor H.C. Verma is the coordinator of that.
Okay.
So this is something which is going on right now. And we are calling it as Physics Bharat Yatra. So we started from Jammu and Kashmir, we went to Ladakh, then we were in Himachal. So I was very happy to be in some programs within Himachal Pradesh. And now it went to Uttarakhand, and now it is trying to move towards Delhi and Uttar Pradesh. I
Right.
think these are some of the lessons which we need to really carry forward. And we don't mind going to government schools in the remotest of the parts of the country. People are creating small ideas. Very interesting competitions are being organized. We have number of competitions in IAPT where I think some kind of inputs, if we can really get from organizations like IUPAP and some kind of support as is being given to us in ICPE, uh, thanks to Professor Grover, who has been our mentor in this effort. I hope that we are going to have a very good ICPE 2025 in IIT Ropar and IISER Mohali. IAPT is there in the cloud, and we are very
Correct.
active in the cloud itself. And I am happy that you are very much willing to be part of that, and you have accepted our invitation. And really would love to really interact more and more with you. और आपका जो हिंदी वाला था इसमें एक जिक्र, तो मुझे बहुत अच्छा लगा.
जी.
हमको हमारी जो नेशनल एजुकेशन पॉलिसी है 2020, उसमें हमारी जो लैंग्वेजेस हैं, लोकल लैंग्वेजेस, वर्नेकुलर लैंग्वेजेस, उसके ऊपर बहुत जोर है, स्ट्रेस है
हाँ जी.
कि आप उस पर बात करना शुरू करें. और आजकल तो कुछ भी दूर नहीं है, आप अंग्रेजी में बोलिए, इमीडिएटली हिंदी में ट्रांसलेट हो जाता है, हिंदी में
हाँ जी.
बोलिए, अंग्रेजी में ट्रांसलेट हो जाता है. तो मेरे को
करेक्ट.
लगता है
करेक्ट.
हमारे पास बहुत अपॉर्चुनिटीज हैं, और शायद हमारे पास और हाथ चाहिए ये सब काम करने के लिए. और
तो
मेरा ये
जी.
मानना है कि आपके इस लेक्चर से हमारी कम्युनिटी खूब इंस्पायर होगी और काफी अच्छा करने की कोशिश भी करेगी. थैंक यू वेरी वेरी मच.
Thank you, Professor Ahluwalia. I 100% agree. Yeah, as far as IUPAP is concerned, any good idea you have, please do share. Our job is to ensure spread of physics education, enable physics education. And as I mentioned, all the, the emerging talent is in countries like India, right? Today, maybe it is close to 40-50% of youngsters are in India. And that number is going to grow, while elsewhere it will decline. So anything we ask, it is very easy to convince my colleagues in executive council that this is something worth supporting. And if, for example, you need access to some conferences, etc., we can think of mechanism by which, because nowadays through online tools, everything can be made available. So that is something we can do. I forgot to mention one thing, which I alluded to in the beginning. You see, Professor Ting told me something very interesting. When he proposed the experiment, which ultimately led to the discovery of J particle in 1974, his proposal to do that experiment was rejected by all the leading laboratories in USA. The funding agencies didn't approve. Finally, he couched his proposal in a very conventional terms, that he is looking for something very ordinary. What he had proposed was he was looking for something quite revolutionary, and that got you see, when you propose something which looks very challenging, then people don't believe you. They think that you are आप बहुत ऊपर की सोच रहे हैं, ऐसा कुछ हो नहीं पाएगा. So your proposal. So he instead of saying that he is searching for heavier bosons, etc., he said he is looking for cross section for muon pairs, invariant mass distribution of muon pairs, which is a run-of-the-mill problem. And even then, only Brookhaven National Lab, which is not the top lab of that era, approved it. And he discovered the J boson. Of course, then everything changed. And before that, when he did his PhD, there was a report that, you remember for the quantum electrodynamics, theory of quantum electrodynamics, Feynman, Tominaga, and Schwinger were awarded Nobel Prize in 1965. And then around that time, just after that, there was a report by two experiments, one a group from Cornell, another from, I think, from Harvard, which said that the electron has finite size, which cast doubts on QED, because according to QED, the electron has zero size, it has no structure. So Professor Ting proposed that he would like to test this idea with a higher sensitivity. And his proposal was soundly rejected in the United States, where he had studied and he had done his PhD and all that. So he decided to explore other avenues, and he found out there's a new lab has opened in Germany called DAISY. So he applied there. Germans anyway wanted people to come, so they said, "आ जाओ, कर लो अपना experiment." तो वो पहुंच गए वहां उन्होंने experiment किया, and his sensitivity was 10,000 times higher than the previous experiment. And he showed it is background events which are masquerading as finite size electron, because they were not able to reject the background as efficiently as they claimed. So he did that experiment and came back to United States and went to the high energy physics conference and requested the chairman, who happened to be Keith Penofsky, that give me some time, I want to present these results. And he said, "Oh, you have come late, but I'll give you 10 minutes since you have come all the way from Germany." In 5 minutes, he explained how his detector works, and the last 5 minutes he presented. And it so happened Feynman was sitting in the audience, and he was absolutely blown away. So he came to Professor Ting and told him that this is an amazing experiment you have done. And he said after that he became his best friend, and so much so that every time he wanted to do an experiment, he'll go and talk to Feynman, and Feynman will give his opinion. And when he won the Nobel Prize, Feynman sent him a telegram saying that, "Congratulations, Sam, you have won the Nobel Prize. Now all kinds of people will come and ask you to speak on all kinds of topics that you know nothing about. So don't accept those invitations and don't make a fool of yourself. Stick to your physics. That is what you are good at." So Professor Ting told me that he has never forgotten that advice, which was given in 1976. So anytime you ask him on anything other than what his subject is, he'll say, "I'm not qualified to speak." So he sticks to his physics, and that's it. He will not deviate. If you ask him about quantum computing, about climate change, he will say, "No, I'm not competent." He's competent. He can speak, but he won't speak. So I thought I should share this story that,
Yes,
how people, and at the age of 89, he's as focused, probably more focused than any 20-year-old or 25-year-old.
Thank you. Thank you very much. Professor Grover, please.
Hello. So what can I tell you at the end of a very fascinating talk? And after the talk, two more fascinating anecdotes that Sunil described to us. I'm just tempted to recall for you Bhabha himself would have been very, very happy to see someone from the school that he created and the purposes for the school that he created has reached the position he once occupied as the president of IUPAC. See, Bhabha, when he proposed the creation of uh, TIFR, at that time, the Indian scientific community had held a symposium in September of 1943, and the topic allotted to Bhabha was allocation of scientific research to the universities. So he went on to create atomic energy program, space program, and so on and so forth. But before the proposal of the Tata Institute of Fundamental Research, his focus was on what should happen in the universities of India. And that is 2 years before even the war ended. So whatever Bhabha contributed to that symposium, that stands published in the Proceedings of National Institute of Sciences, 1944. And let me read out few lines from that extract. He said, one should look upon pure research as a long-time research, while technical research, being historically the later stage in any line of development, may be looked upon as a short-term research. Long-term research would appear in general best carried out in the universities or in special institutes attached to the universities. So TIFR, when it was created, was supposed to be embedded in the University of Bombay. Okay, it was supposed to work in partnership with the University Physics Department. He says, research on subjects where the possibilities of applications are still so remote that it is impossible to foresee them are clearly best carried out in the universities. I think this statement of Bhabha is very, very important. Today, when there is all the time asking for returns on the research being done at the end of 3 years, obviously we are deviating from the spirit in which the research was supposed to be supported in the universities of India. Bhabha went on to add that no country which wishes to play a leading part in the world can afford to neglect pure or long-term research, for it is precisely on this research that depend the developments in industry and public economy which are likely to take place, say, 25 years hence. Then he further adds, there is no genuine knowledge of the universe that is not potentially useful for man, not merely in the sense that action may one day be taken on it, but also in the fact that every new knowledge necessarily affects the way in which we hold all the rest of our work. So Sunil, when carried out the research under this Grapes 3 experiment, this was extension of a lab that was set up by Bhabha's visit to Ooty itself. When Bhabha visited Ooty to set up the cosmic research lab there, Professor Shirikanthan had accompanied him as a young colleague. So it is, this at Ooty it was research on the ground, but in Kolar Goldfields it was research deep inside. But the instruments which were built up for doing research deep inside the earth, those instruments actually became a part of the instruments that Sunil used as a Grapes 3 in his muon telescope. So you see all this, it's a long time research, fundamental research, which has to be supported on its own stream. It is not only the research which has to be supported on its own stream, but all the development efforts which have to be supported all along. And also the leaders who are leading this research, you also have to have confidence in them. You have not to frustrate them by asking, what is your output over last 6 months? What is your output over last 1 year? If Sunil had not continued this for 20 years, okay, in a spirited way and carried all the team with him, You think the first PRL that came 15 years after the grapes tree was started would have come. And that is the experiment which got reported globally in the maximum number of media reports. I don't think there is any experiment from India in the post-independent era which has attracted that much of universal attention. The second TRL of Sunil, which is related to these thunderstorms, nobody would ever have thought that this basic research experiments can give you something which will have potential societal benefit. The experiments are not set up for this. But as Baba said, there is no genuine knowledge of the universe that is not potentially useful for man. So I think it is a beautiful exemplification. And if Baba was alive today, he would have been the most delighted person. So, I mean, persons like Sunil, when they joined TIFR, he was taken in as a research training in the year 1976 by Professor Shrikantan, who saw that the main USP of TIFR was supporting this long-term fundamental research which has a long gestation period. And he felt that that was suffering, that had started to suffer because we started a graduate school, which in most other disciplines is okay. But many of the USPs of TIFR, like building radio telescope, building this, detectors which have to be put underground and data has to be collected over a long period of time, or building astrosat. It takes 5 years to build instrument for astrosat, then it takes 5 years to collect data for this thing. So unless you support all these things, how will those things happen? So those things have started to suffer. So Professor Shrikandan came up with the scheme because he himself was inducted by Bhabha initially as a research assistant. But after a few years, he was given a free hand to work without worrying as to when his experiment will come to an end. So Shrikandan said the time had come that a fresh blood should be inducted into TIFR. So Shrikandan inducted some 20 odd young people into TIFR to support the USP of TIFR. That means support programs which require a long gestation period. Now, in order to have this thing being accepted with the rest of the TIFR, he allowed some other groups who are into short-term research also to induct some people. So I was a beneficiary of that change in plan that Srikandan put in. And though I was not working on the kind of things that radio astronomy or high energy cosmic rays, deep underground, or like a UT experiment, but I was in a condensed matter group, but I was also inducted by Professor Shrikantan as a research associate. And in fact, Professor KP Singh, who built this X-ray telescope, Professor Rao, who also built another telescope, they are all inducted in that era. Or Professor Pillai, who built the superconducting LINAC for TIFR, which was extension of the accelerator that was bought, Pelletron. So Pelletron had a limited life, but if you have to extend its life, you have to build a superconducting LINAC attached to it. But who will build it? It takes so many years of research before you can build it. So many of us who got inducted into TIFR, all of us are now retired because people inducted in the year 1976, 77, 78. It is, they have lived 40 years, have gone since five. So I thought I will just share with you that we should continue to support this kind of a research. I hope the thought leaders and the scientific leadership in India, which is managing the Anusandhan National Research Foundation and supporting the mission-oriented research, which is very important. The whole of atomic energy program is mission-oriented research. But side by side, the mission-oriented research, a small fraction of the total money
Budget.
that nation or the corporate sector in this country can afford, that should be set aside for research of the kind that Baba had envisaged in fundamental sciences, and also the mathematics, which he thought was very, very important, because in that 43 is write-up of Baba, he writes, long-term research should include pure mathematics, which, as the last century has shown, have turned out to be the most unexpected, which have to be of most unexpected importance in formulating the laws of nature and in solving practical problems. It was
Yes.
stated by Baba, 1943, before even the Gauravji Tata Trust has met to evaluate the first letter which reached them in March of 1944. 6 months after Baba wrote all these things in September of 1943. So thank you, Professor Ahluwalia, for giving me a chance to just describe
Uh,
and taking
yeah.
these things off my chest. Thank you.
Can I add one more comment to what Professor Grover said? You see, just like Bhava, Professor Grover also has been a visionary. It is very remarkable that even in the department that I worked in, people were highly skeptical because everybody wanted quick output, you know. So one of the passion was to join a high energy physics experiment happening in Fermilab or CERN somewhere, where already hundreds and thousands of people are working, instruments are running, data is coming out, people are just analyzing and publishing papers. But Professor Grover was one of the rare personalities. Despite him not being from this field, he recognized the importance of this field. He recognized the long-term nature of it. So I will just add one or two more examples. See, when we were doing all these development activities, you know, we had to develop instruments. How do we do that? We had some scientific staff. We call them scientific staff because primarily they are engineers. They are the electrical engineers, electronics engineers, or mechanical engineers. They help us in designing and developing those instruments. Now, these people, some of them have stayed on, some of them left. Those who left have gone into industry, have done fabulously well because they were solving real life problems, which is what industry desperately needs. Similarly, in 2010, one of our colleagues who joined the engineering college in Pune came to me and said, I want you to train some of our students. And his logic was very simple. He said that most of the people who come to engineering come because of the promise that at the end of 4 years, they'll get a nice package. But when they start studying engineering, they find that is not their cup of tea. They don't like engineering so much. They would rather like something which is more stimulating. So such people want to have research-oriented projects. So he said, can you give projects? I said, look, if I just give projects, it's a one-way street because we have to give project. That person will write the project report. We have to correct it. Then he or she will apply for a position. We have to send recommendation letters. My colleagues get frustrated that what are we getting in return? So I said, let us have a different model. We'll not assign project to students. We'll assign project to one of your faculty. You please identify that faculty member, either electronic circuit or a software tool to be developed. One batch of students will come and start working on that project. They'll reach some level of completion, maybe not complete. And they will write the report and move on. We'll guide them, we'll provide the equipment. And then second batch will come and take off where the previous batch has left off and continue. So between 2 to 3 years, most of the projects got completed. As a consequence, you know, it happened that we were always able to, not every project, but about 30 to 40% of the projects got completed. So we were able to develop tremendous amount of, technology through that route, which was not available to us, which would have costed us a fortune. So, and not to great surprise, the students we trained who did these kind of projects were the first to be hired by industry because no industrialist wants a theoretical engineer. They want an engineer who can solve practical problems. And we gave them training to solve practical problems. And I will tell you, I'm not belittling anybody's contribution. Initially, when we started, we'll give a project, the faculty member will come and say, sir, we have solved everything. Then I would reply, look, it is not possible to solve everything. Maybe only God can solve everything. But those human beings, if you try to develop a circuit or do something will work, but something will not function. And we probed and found that actually that was not the case. They put together some circuit, but they have not tested it. When you test, that is when you find out that it does the job or not. Now you test it under certain ideal condition, it works. But you test it under more extreme condition, it does not work. But the actual instrument has to work in all kinds of conditions. So that kind of training, which is driven by practical requirements, is very different from just classroom or blackboard teaching. So this is something which I think added great deal of value. So during that 10 years of that project, we trained 200 engineers. And many of them went into research either in India or abroad. Some of them even joined TIFR. And a very large number of them went to Indian industry, where they became superstars of that particular organization, because they rose very rapidly in the hierarchy. And I still get emails from them from time to time when they have some landmark cross that we have done this, we have done that. And, so what I'm saying is these kind of projects have other spin-offs, which are immeasurable, in terms of, and the confidence it gives to people. You solve a real problem, that boosts your confidence, that no amount of writing papers and reports is going to get you. The real problem solving can get you, So this is something I want to share with you. And it's thanks to people like Professor Grover, who were just, he stood like a rock. I cannot express my thanks enough. He stood up to the management and all that when they were not too happy about it, because they were all wanted quick results. None of them were interested in long-term thinking, So he was one of the few people, and a couple of others. And it helped the fact that I was in Ooty, not in Mumbai. So nobody knew what I was doing. It helped. A distance of 1,000 kilometers did help to some extent.
Thank you. So for this program of the webinar series, Professor VP Singh was also very much instrumental in curating the talks and giving us ideas. I would like to request him to please come and say and share his thoughts.
Thank you very much. First of all, I would like to thank Professor Gupta for a wonderful talk, and it was really, I just put down in this chat box also, it was a mesmerizing talk, in fact. And you have given a detailed journey from the student days to maybe the journey will continue. We hope that it will continue in the better and better way. And we wish you very good success in life as well. And it is not only, I can just see that the way you built this UT, this grapes 3 experimental setup over there, it was really like you have worked like an institution builder. It is one of those kind in India itself. I mean, and everybody will appreciate. And you are also associated with our department as well. And there are groups and some students also work with you. And they always praise you like anything, like how you support them, how you teach them, how you tell how to do many other things. So once again, I will not take so much time because it is already a short of time. Thank you so much for accepting our invitation to participate in this program and giving us many detailed insight to us. And we are really proud of the people like you or the scientists like you, I will say. Thank you so much, sir. Thank you so much.
Thank you very much. It is a pleasure and honor to be with you, with all of you. Thank you.
Professor Manoj, please, over to you.
Thank you, sir. Now I request Professor DC Gupta, sir, our formally vote of thanks. This is just a formality, but Professor DC Gupta, sir.
प्लीज अपने को अनम्यूट करिए गुप्ता जी.
Thank you, sir, Manoj sir, for giving me this opportunity. And it was a great talk and a good series, which was organized by IAPT RC4 monthly webinar series of IAPT to celebrate IYQ 2025. And for me, this day was very nice day to learn something from Professor Gupta, that how good teachers can frame a whole generation, because what he's teaching just to impart practical knowledge, only not theoretical. Because nowadays what is happening in institutes also, that people are going like just doing physics, like solving numerical problems and getting over the competitions. But real life problem, as he told that he was creating their experiments and doing by himself, and they were devising the circuits and some sort of experimental instruments. So that is needed today. And I ask him, I would urge him that our IPT should move toward this, that how we can impart this attitude or this type of inclination in our students, and how this can be benefited for our students of 10+2, so that we can inculcate a better practical plus theoretical knowledge in them, in our students, and as well as teachers. So thank you, all of you, sir, for this nice talks, all 5 talks which we have carried over. And I especially want to thank Professor Gupta today, and Arun Grover, sir, Ajay Ghatak, sir, BP Singh, sir, Professor Aluwalia, Sundar Singh ji, and Sri Manobhushan Pandey ji, along with Sanjay, sir. So thank you all for organizing such a nice workshop and very interesting lifetimes experiences which you have carried out, that would be beneficial for all of us. Thank you, all of you, sir.
Thank you. Thank you very much.
So thank you, Professor Sunil. So you will have more opportunities to come and talk. Thank you very much.
Sure. Surely.
So we can now end the session. I am
Thank you so
signing
much.
off now.
Thank you so
very
much.
much.
Thank you so much.
Okay.